This theorem is called the form of a convergent power series. It talks about a function f represented by a power series. So if f is represented by a power series, and we know what that looks like, f of x is the sum of a sub n x minus c to the n centered about c. So for all x, this representation works for all x in some open interval I, which contains that point C. Then we know that each coefficient a sub n is the nth derivative of the function evaluated at c over n factorial. And then we can represent the function by f of x as f of c plus the derivative at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared, and so on, including the nth derivative evaluated at c over n factorial x minus c to the nth power, and continuing on forever. It's an infinite series. Since we are approximating a function, we cannot assume that all series will converge to the function for all x. That is a problem, we're not sure. So we need to determine the interval in which a series converges to f of x. And this will be different from the interval converging for the series. So we have a convergence for the series that we know that it converges. We know the series converges, but does it actually converge to the function that we're trying to approximate? So we have a theorem called the convergence of a Taylor series. So this talks about when it works. And it says if the limit of the remainder, as n goes to infinity, of the remainder is 0 for all x in my interval, then the Taylor series that I wrote for x converges and actually equals the function I'm trying to approximate. And then we say that f of x equals that series. So we have certain guidelines for finding a Taylor series. So the first thing we want to do is differentiate f and evaluate it at c. So I have f of c, the first derivative at c, the second derivative at c, and so on, nth derivative at c, how many ever we need. And we're going to look for a pattern. In the values that we've gotten. So after that, we're going to use our sequence developed to form the Taylor coefficients. The sequence is up here, these functions evaluated at c. going to form those Taylor coefficients. A sub n, and remember they equal the nth derivative evaluated at c over n factorial. And then we have to determine the interval of convergence for this power series. And that's f of c plus f prime at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared, and on like we've been doing before. And then when we look at that, we're going to look at that interval of convergence. So within this interval of convergence that we found for the power series, we have to see if the series actually converges to the function that we're trying to approximate. So we're going to use those in some examples.